Welcome to section 510 on improper integrals. As I mentioned in class, this term improper is a little bit unfortunate in that there's really nothing wrong with these. They're just different, and that term improper might throw you off, suggesting that something's wrong. It's just that we need to treat them a little differently. So let's jump in and look at the first kind of improper integral, and these are known as infinite interval integrals. Infinite interval integrals. The book refers to them as type 1. And type 1s are easy to spot because either one or both of the limits involves infinity. In these cases, of course, the interval of integration is said to be an infinite interval. So let's take a look at how we're going to handle this kind of thing. And example 1 is sort of the typical problem here. And notice the statement, and type 1s are easy to spot because either the upper limit or the lower limit or both are going to involve an infinity. And of course, if we went and simply calculated the antiderivative, it'd be difficult for us to put in infinity. In fact, impossible. So this is how we're going to handle them. Whenever we run into this kind of integral, we're going to treat it like a limit problem. And so it'll be proper for us to write that it equals the limit, and we'll just pick a variable, typically t, and we'll say as t approaches infinity, and we'll let the limit go from 1 to t, not from 1 to infinity. So we'll proceed as before. That is to say, we'll take the antiderivative of 1 over x squared, and of course that is what, x to the negative 2, and that antiderivative is suggests an antiderivative of what, x to the negative 1 over negative 1, may be better stated as negative 1 over x. So I've got that right here, negative 1 over x. Our upper limit is t, our lower limit is 1. I go ahead and plug those in, right? And now I think about, well, before I did that, I thought, you know, this is minus a minus. Let's just flip these terms and make this minus a minus 1, 1. 1 minus 1 over t. Just a little easier on the eyes, I think. And think about this now as t goes to infinity. Of course, this entire fraction goes to 0. And 1 minus 0, of course, is 1. And we say that this integral converges. That is, it sums up or totals, and it converges to the number 1. Let's take a look at yet another example. This time, and these instructions are typical, the same ones used in the book, determine if the following integral is convergent or divergent. Convergent means that it sums to a total. Divergent means that it goes to infinity and there is no total or answer. So the instructions will say determine if it's convergent or divergent. We'll start using the letters C, capital C, or D to indicate convergence or divergence. And we're asked that if it's convergent to solve for its value. So the integral says, and it's type 1 again because you see this infinity in one of the limits. So we're going to change this and say this is really a limit problem as t goes to infinity, and we'll rewrite the integral as 1 to t. So the antiderivative of 1 over x, of course, is the natural log of x. And our upper limit would be t and our lower limit 1. So we would write the natural log of t minus the natural log of 1, which is 0. But as t goes to infinity, the natural log of infinity goes to infinity. So the limit is infinite, and therefore we say the integral is divergent, or just big D, and we're done. There is no value to be found. I can't help myself but point out at this point that whenever we have an integral of this form, 1 over x, and that power, that p-value, when that p-value is less than or equal to 1, in this case that we just did, it was exactly 1, this kind of integral will always be divergent if that p, that power, is less than or equal to 1. But if it's greater than 1, it will converge. And this is a fact that we'll use later in Chapter 8. Can't help myself for bringing it up now. Let's take a look at yet another example. Here's one where there's an infinity now in the lower limit. We see it negative infinity to 0. Again, a type 1, easy to spot. These are the ones where the interval is infinite, right? So we're going to rewrite that. We're going to put t now down in the denominator, and we're going to say as that lower limit goes to negative infinity up to 0. And then we're going to take and find the integrand of all of that. Well, with a little substitution, and I'll allow you to go off to the side and check me, but with a little substitution for 3 minus x, you can solve this integral pretty easily, and that antiderivative is negative 2 times the square root of 3 minus x. Remember, our upper limit is 0, our lower limit is t, and we're interested in t going to negative infinity. So we put the upper limit in, and of course we get negative 2 times radical 3, and that looks good. We put the lower limit in, or we at least think about that. As t goes to negative infinity, this number under the radical sign will go to infinity. And twice infinity, of course, is infinity. And anything plus infinity is also infinity. So the limit's infinite, and this integral is said to be divergent. There's no value to be found. So big D on the end of that one, and we're done. Another example. Here is a type 1, and this time we have an infinity not in one, but in both limits. And the trick here is to take and to split it. And I think you'll agree that if we go from negative infinity to 0, we can pick up and say, let's add to it and start at 0 and take it to positive infinity. So we can take this integral and split it into 2 integrals. Now we have twice the fun. We have the opportunity to evaluate 2 integrals. So I've split them. On the left, I took this integral negative infinity to 0, and I rewrote it as a limit, t going to negative infinity, replaced t down below as my lower limit. Now I've come at it, and again with this time voodoo, I've evaluated the limit, and the limit happens to be negative 1/2 e to the negative 2x power. Well, if I'm going to take that back. I didn't use voodoo. I used a simple substitution. I used u equals negative x squared, and then took the derivative of negative x squared, which would be negative 2u du, and then did the magic. You can check me, but I'm quite sure I did it correctly off to the side. Anyway, not to get off track too far here, but we have this limit as t goes to negative infinity, and there are my upper and lower limits. If I put the upper limit in of 0 and get negative 1/2 e to the 0, I get a negative 1/2 out. If I put my lower limit in, negative infinity, and I take and my minus a minus, I get a plus 1/2 now, e to the negative t squared, and again t is going to go to negative infinity, square it, but it's negative, it's going to go to 0, and so I'm going to get negative 1/2 or plus 0. The whole thing will settle out to negative 1/2. That second integral, again writing it out, taking and writing it as a limit, letting t go to infinity, replacing that upper limit with t, doing the substitution, u equals negative x squared, etc., solving the integral, evaluating now with t and 0, letting that upper limit go to t negative t squared, where t is going to infinity. That whole term is going to go to 0. You're going to get negative 1 over 2 times 1 over e going to infinity, and it's going to take it to 0. And 0 plus 1/2 is 1/2. Now we're going to take those two results from those two pieces and say, well, this guy that I split into a sum of two integrals whose evaluations were negative and 1/2 and positive 1/2 respectively, when I brought them together gave me 0, and we would say this integral converges to the value 0. One more example before we look at the second type. And this type, let's say we have negative 2 to infinity integral of the sine of x. So we'll rewrite it as we'll take the infinity out, put in t, put the limit as t approaches. Now we'll take the integral of sine, which is negative cosine, our upper and lower limits respectively. Now I changed it around because when I put in, it just seems to me to be cleaner to write it this way. Minus a minus will become plus, so I'll put the cosine of 2 first right away, and then I'll have the minus cosine of t. As t goes to infinity, this part never settles down. It doesn't go towards a target, right? It keeps going between 1 and negative 1 forever. Therefore, we would say this is divergent. It doesn't exist. Therefore, the limit cannot be solved. There is no value that it's converging to. Now let's look at the other type. And the other type is called a discontinuous integrand. I call it the sneaky type. type 2 is what the book calls it. And these are integrals where the integrand it has a discontinuity over the interval. For example, take a look at example 6. Sometimes it happens at the endpoints, and sometimes it happens at somewhere between the ends. You know, if you put 0 in this denominator, it's not a problem. But if you put the other endpoint in, that is 3, you have a problem. You have 1 over 0, which doesn't make sense, where there's a discontinuity, we'd say, in the integrand. There's a discontinuity at 3. So the way we handle it is similar to what we did before. This time, again, we'd write it. We'd take the problem value out, the 3, and we'd put t in. And now we take a limit and we'd say, you know, it's as t approaches 3, and to be technically correct, we're approaching 3 from the left. We're going from 0 to 3. From that 0 side, we're coming from the left at 3. So now we take and evaluate again with a little substitution. I did this problem, same problem earlier, so we won't get into the mechanics. You can check, you can pause and check if you want. Anyway, we're going to think now about putting in our upper and lower limits, t and 0 respectively. So I've twisted it around a little bit. You know, my lower limit would mean minus a minus, so I brought that out front and said, hey, that's going to be 2 radical 3, the positive. And the first part of it will be negative, and it'll have the t in it, right? So that's that part. I hope that doesn't confuse you too much. Just saving a little time and a little space. Anyway, can't I put 3 in using direct substitution? Isn't radical 0 make sense? It is 0, and 2 times 0, of course, is 0, and minus a 0 makes sense. So the whole thing converges, we say, to 2 radical 3. This limit exists. The integral, we say, converges to the term or the value 2 radical 3. Another example. And here's one where there's not an issue at the lower limit. You can take and cube a negative 2. There's not a limit at a problem at the upper limit. You can put in 3 and cube it. 1 over 27 is not a problem. But this one's very sneaky. Between those two values, negative 2 and 3, lies the number 0, where there's a problem. So we take this guy and we split it at the problem value. We say, how about going from negative 2 to 0 and then picking up at 0 and continuing to 3? So let's start with this first one and think about what that would be. And wouldn't the evaluation of that integral be negative 1 over 2x squared? Now, I'm going at 0, you know, from negative 2 to 0. I'm going to 0 from the left. I've replaced the upper and lower bound, the upper bound rather, with t. And now I'm thinking about what happens as we go at 0. In other words, as this value t goes at 0, this denominator gets very, very small, forcing itself into the numerator more and more times. The smaller the 2t squared gets, the bigger this value gets. In fact, it gets just more and more negative. It completely obliterates 1/8. This is going to negative infinity. Now, at this point, once we've established that this first half the problem is divergent, we're done. we don't have to continue. If the first part is divergent, it means the entire integral is divergent. Don't get the idea that if we come over to this second part, and I'm not even going to do it, but let's just say that we worked it out and it worked out to be positive infinity, that somehow we'd say, well, the first part was negative infinity, the second part's positive infinity, so we can take these two undefined quantities and add them together and somehow say they equal 0. Well, they don't. So this is a case where we don't even need to work that second integral. We're finished as soon as we find that any part of it is undefined or infinite. I think I have one more here. No, I don't. And that was more than enough. It's over 20 minutes. So I'm going to let you take a look at these problems. And these problems are coming from page 421. And there are a slew of them there. And I would like you to certainly do numbers 1 and 2. That is, to look at those and to think about, either why are they improper or are they improper? Why or why not? So do numbers 1 and 2. And then jump in with number 5. And, if it's divergent, you're done. There's no need to find the value. If they're convergent, find what it converges to. So let's take 5 and let's take it to 33. Let's do the odds. 5 to 33 odds. And be ready to talk about those the next time we get together. So that's 5 to 33 odd. Thank you.